In our last video, we talked about the idea of partial fractions, and we're going to get to the method there and how to do that. But the problem is that the method of partial fractions, or partial fraction decomposition, is only really valid if the polynomial on top has a degree less than the polynomial on bottom. So we're going to talk about a method to reduce, or to sort of prepare it or put it in that form so that we can deal with it. And what we'll end up with is this leftover polynomial. But polynomials are easy to antiderive, right? You just use the power rule, add 1 to the power and divide. So anyway, more formally what we can say is this. If I've got two polynomials n of x and d of x, and they're in some sort of quotient here, right? So there's some sort of rational expression. And the degree of n of x is greater than the degree, or equal to the degree of d of x. So think about this in terms of a numerator and denominator. So if the degree of the polynomial in the numerator is greater than the degree of the numerator, or greater than or equal to the degree of the polynomial in the denominator, we can rewrite this in this form. So d of x doesn't change, but instead of n, I now have this r and this q. So what we can think of this as is just like division. If you remember when you divide a number, two numbers, you get some quotient, right? Some number that comes out, and you have a remainder. So you have a quotient and a remainder term. So it's something that comes out even and something that doesn't come out even. It's kind of a, it's a sliver or a fraction of it. And you can always rewrite that number in terms of the quotient plus the remainder over the divisor or the denominator. So this is what we're trying to do. We're going to split out some term, and we're going to have some leftover polynomial where that polynomial is strictly less than the degree of d of x. So that's the goal. The goal is really to set this thing up to be used with partial fractions. So let's get into it. It's a pretty simple process. It's just like long division, so hopefully you're familiar enough with long division from way back in your math career to feel comfortable setting this up. So let's take a look. I have this quotient, or I have this rational expression here. So I have a degree 3 polynomial on top and a degree 2 polynomial on bottom. So how do I deal with the fact that those are disparate degrees? Well, what I'm going to do is I'm going to take the bottom and set that up like, the divisor. And then I'm going to set that up here as the thing I'm going to go into. And you do just like you would do with long division, right? And when you do long division, you say, all right, how many times can this go into that? What we're going to do is do that with the leading term. We basically say, all right, I don't actually care about these for the sake of figuring out my number. I don't care. I just take x squared here, and I say, what times this equals that? Well, it's 2x. So 2x times x squared equals 2x cubed. All I'm trying to do is figure out what times this equals that. So 2x. So once I've figured out what that polynomial is, or what that monomial term is here, I take this and then multiply it by every term. So I multiply it by x squared to get 2x cubed. I multiply it by negative 6x to get negative 12x squared. And I multiply it by negative 40 to get negative 80x. So the key here is to know if you've done this right, is that these terms had better match. If these terms don't match, then you've already done something wrong, but they should match. Then, just like in long division, if you remember how you do long division, you multiply what's here times the number, but you have to subtract it, right? You write it there, but then you have that little minus subtract. But the difference is, instead of just turning it negative like you normally would, you have to distribute that negative because this is a group. So if I end up with a negative 2x cubed, end up with a positive 12x squared, end up with a positive 80x. So then when I add these two together, that term vanishes, which is what you should expect. Negative 15 plus 12 is negative 3. Negative 79 plus 80 is positive 1x. And then the 39 just comes down because it wasn't part of this, right? It's just sort of along for the ride, just like in normal long division. So then this is my new term. This is my new, okay, now what do I do? Well, I say, what times this equals that? So they have the same degree. So I say, okay, well, all I need is a negative 3. So I need a negative 3 here. So once I've figured out what I need, I multiply it by every single term. So I do negative 3 times x squared. So that's negative 3x squared. Negative 3 times negative 6x is a positive 18x. Negative 3 times negative 40 is a positive 120. But again, remember, I have to subtract the polynomial. These things match, so I feel pretty good about what I did. Once I subtract the polynomial, if I distribute, that becomes a positive, that becomes a negative, that becomes a negative. So when we add these together, it's negative and positive, so it goes to 0. 1 minus 18 is minus 17. 39 minus 120 is minus 81. So now I take a look at this one more time and I go, okay, is the degree of this smaller than the degree of that? And the answer is yes. So since it is smaller, strictly less than, I can stop. So again, you keep going until you have to stop. It's not very useful, keep going until you have to stop. But the idea is, when this degree is strictly less than that degree, you know you can stop. So the question becomes, all right, what do I do? Well, I have two things I've generated. I've generated this piece, and I've generated that piece. Well, this piece is that q of x term, because that's what divided out evenly, and this is the remainder term. So that goes on top of that, on top of the dividing polynomial. Now, if you wanted to get a common denominator, I wouldn't recommend this, but if you've got a common denominator and then added it all together and simplified it, you just get this, right? So you're wasting your time getting a common denominator. But the point of doing this is that if I have an integral that I'm solving for here, I now have an integral of this and that. Well, I can do the integral of this all day, right? That's about the easiest integral in the world. And then this integral, we have to decide what we're going to do with it. We have to decide if we're going to use u substitution, trigonometric substitution, or partial fraction decomposition. And in this case, I would say partial fraction decomposition makes the most sense, but we'll get there as we move on to an additional video.